Welcome back to today's tutorial. In today's tutorial, we're going to discuss training our data using the linear regression model in scikit-learn. Before we get today's video, make sure you hit the subscribe button down below and like the video for more content just like this. Let's get right into it. All right, so let's talk about the linear regression model. So up to this point, what we've been doing is we've been altering our housing data frame object. We've gone through stratifying our data, separating our data into a test set, as well as a training set, how to visualize our data, how to notice trends in our data. More recently, we've been discussing how to transform our data using transformers, how to use pipelines, how to use the column transformer. We've gotten into all of that. And at this point, we have a good training set in order to give to our model. And so now we're going to begin the process of actually using that training set in order to train our model. Let's take a look at the training set that we were able to prepare in the last lesson in particular. We were able to prepare a dense matrix basically that had all the data stratified between -3 and 3 using the standard scalar transformer in the scikit-learn library, as well as this particular this data that we have here is data that, remember, we have used the simple imputer transformer in order to fill in missing values with the median of that particular column, as well as we were able to convert the categorical data, which is alphabetical data, into data that we can understand by converting it into ones and zeros, essentially, right? By converting that data that's categorical using the one-hot encoder class. And so we were able to do a lot of that different work, and this was very helpful for us. Now, at this point, what we have here is we have a good training set that we can use in order to train our model. And so let's take a look at how we can train our model using scikit-learn. So using scikit-learn, we're going to begin by talking about the linear regression model. Now, we're going to go and learn about linear regression model, and then from there, we're going to learn another model as well. But we're going to start with the linear regression model as our base model because it is a fairly easy model to understand. And then we're going to analyze a little bit about the output of this model. And even in the next lesson, we'll learn how accurate this model was. But even in today's lesson, we'll discuss using a small sample size how accurate the model was. So first of all, let's discuss linear regression. What is linear regression? Well, linear regression is basically trying to predict a line, right, such that we can basically take into consideration as many data values as possible. And so what's the process of this? Well, first of all, we have an equation in the form of y equals w times x sub 1, w2 times x sub 2, w3 times x sub 3, plus some value of b. The x in this case will represent each attribute. The w will represent the importance of each attribute. So in this case, we have how many attributes? We have roughly 10 attributes. And so we're going to have roughly 10 variables. The w will represent the importance of each attribute. It will simply be a coefficient that is in front of each particular attribute that will represent the accuracy, or the weight rather, of each particular attribute. The b represents a bias, and that's simply the y-intercept, right? So where it's beginning. All right, and then the b, that's the b, and then the y will represent what we want as our output. So using all these attributes, as well as the weights for each of these attributes, what is going to be our predicted output, or our predicted house price in this particular case? So that's what this is going to do. That's the form of the equation that the linear regression model is going to do. Now, what is the steps it's going to do in order to accomplish this? What it's first going to do is it's first going to start off with random weights. And really the goal out of all of this really is to adjust these W values, these weights, in order to minimize the error. That's the main goal. How can we adjust these weights in order to minimize the error? But we're going to start off with random weights. And then from there, we're going to make predictions using those random weights. So the model is going to do this, by the way. The model is going to do this, but we're just going through the background in terms of what the model is doing behind the scenes. But the model is going to make predictions using those random weights of what the house value is going to be. And then when it makes predictions, it's going to measure the error. Now, what is the error? Well, the error is the difference between the projected error that their equation has projected compared to the actual label of what it's supposed to project. And it's going to measure that error, and it's going to perform some more mathematical operations on that. But generally speaking, you just need to understand this from a very high level. What it's going to do is it's going to measure the error and then adjust those weights based on what the error is. And so if the error is very high, it might say, okay, we might want to lower this weight or increase this particular weight in order to make the model better. And it's going to repeat this process many times in order to minimize that error, checking the error every time it does this. So that's what the linear regression model does in a very high level. And again, this is not, we're not going very too in depth into the mathematical basis behind this, but you should understand, just generally speaking, what does a linear regression model do? So that way you're going to be able to compare it to different models. So you don't need to be necessarily the greatest person in math in order to get into this, but you do need to be able to understand, at least from a high level, what all of these different models are providing to us. And this is not very difficult to understand. So that way you can compare it to the different models. Okay. So now let's go ahead and get into the programming for a second. So we're going to import the linear regression model. And so we're going to create a linear regression model instance. And then from there, we're going to call the fit function. So we're going to call the fit function. And we're going to pass in, and remember what the fit function does for a second. So the fit function, if you remember, what it does is, going back up here, it learns the parameters needed from the transformation, such as the median. So it actually, what it does there is it calculates those particular values. And then the transform function applies those transformations to the data set using those learned parameters. And so we saw here how over here, we call the fit transform function when we created our pipeline for the first time. So we can learn, for example, what the median is, how to calculate the standard scalar, and then it applied it in that particular case using the transform function. And the fit transform function allows us to complete both those operations in just one method. But we're going to call the fit function in order for it to learn the data. And what are we going to pass into the data? Well, we're going to pass the housing prepared data. The housing prepared data, let's go ahead and revisit this data for a second. So the housing prepared data, let's go ahead and print it out. And we'll also print out the housing labels, okay? Housing underscore labels. And let's compare this data. Now, if you remember the housing labels, what is our housing label in this case? What are we looking for? What's our Y value in this case for our linear regression model? Well, it is going to be our median house value. That is the value that we are searching for. And all the other values, the X values, will be these particular attributes. Let's go ahead and print out our housing prepared data as well as our labels. So when we print out the housing prepared data, remember the housing prepared data is data that basically is this, right? Is basically data that has been standardized between that interval of -3 to 3. Let's go ahead and print this out now. And so when we print this out, you can see here that we have our housing prepared data, and it is data that is in between an interval of -3 to 3. Now, it actually is typically speaking, is between -3 and 3 unless there's extreme outliers, right? And so that's what we have here for our prepared data. And then we have our housing labels. Our housing labels is data, basically, remember, that is not standardized in any way whatsoever. And this is the way we typically will work with these models. The predictors that are going to go into these models have to be in the same format so the model can understand it. When I say in the same format, I mean it has to be within the same range, right? But the output values, the Y values, it doesn't really matter, right? Because when you think about it, right, the X, though this is the Y axis basically in a graph, right? These are your Y values, and then you're gonna have X values at the bottom, right? So this is kind of how it's like, right? Let me go ahead and put something like that. Okay, this is basically how your graph is gonna look like, right? The X values remember, are the attributes. The attributes have to be in a similar range, right? So that way the model can compare them. But as far as the Y values are concerned, we're only projecting one Y value. Now, if we were trying to project two Y values, then we would want those two Y values to have a similar range within them, right? So let's say we tried to predict not only the median house value, but we also tried to predict the median income. Well, then we would want the median income and the median house value to be in a similar range. But in this case, we're only projecting one particular Y value. And so because of that, the Y values don't necessarily have to be in the same range as the X values do, but the X values do have to be in that same range. Okay, so that's important there. And so that's why we didn't have to standardize our housing labels. Our housing label, remember, is our housing median value. And our housing prepared data, if you also remember that, does not contain a stratified version of our median house value. Because remember, we passed in the last lesson, we passed in the housing data frame, which if I go ahead and create another cell here, let's say I print housing. Remember, housing, before we passed it into this pipeline operation, it was data that did not include the median house value. It only contained the data that was a part of our attributes. So keep that in mind. All right. So with that being said, let's take a look at what we're going to be passing into this particular fit function. So the fit function, remember, learns the parameters in our data, learns those particular parameters. And so we're going to pass in the housing prepared data. Those are your attributes. And the housing labels are simply the outputs of what we want to expect. And what this fit function is going to do is it's going to do everything that we described above. Everything that we described right over here, it's basically doing that. It's going to follow basically in general from a high level of these 5 steps. Now you might be thinking, okay, why do I need to understand these 5 steps? Well, because you want to be able to compare this to different models, right? If you want to decide which model to use. And having a good understanding of what the model is doing behind the scenes is very useful. All right. So now let me go ahead and run this here. And I just put a print statement at the bottom. So you can see it fitted the data fairly fast there. But now I want to look at finding out what the error is and then doing a mean absolute percent error. Okay, let me just get rid of that for a second. All right, so a mean absolute percent error, we'll do that at the very end just to evaluate just some preliminary results here. All right, so what we're gonna go ahead and do is we're not gonna really do we're not gonna go through a very scientific way of calculating how accurate our model was. So now that we have our model, remember, we want our model to predict what the output is gonna be given some inputs, right? That's our goal. We're going to give some inputs and we want the model to predict outputs and we want those outputs to be accurate. That's the goal of our model in essence, right? And so we wanted to basically go to the correct position in the Y. We want to see basically, we want to compare when we have the line, right? A linear line essentially, right? We want to see that if we give a certain X value, the X value will point to a value in the Y value in the graph itself, on the line itself, that is close to the actual value at that particular X value, essentially. And what the model is doing behind the scenes is measuring the difference between what the actual output is and comparing it to the projected output, and it's getting that error. So that's the error that it's going to be going to get. And after it gets that error, it's going to square that error. It's going to perform some mathematical operations on that error. But in general, like from a high level, that's what you need to know. All right. So we're going to go ahead and first of all, what we're going to go ahead and do in order to find the error. Well, in order to find the error, what we would want to do is we want to submit some of our own data and we want to compare it to the labels, right? And we want the model to predict what the model is projecting and then compare that to the actual output in essence. And so we're going to get our data. So the data from housing here, this is the original housing attributes. So let's go ahead and print this out here for a second. So print sum underscore data. This is going to print out the first 5 rows. Okay, the first 5 rows of the table. Let's go ahead and let's see, something's wrong here. Incomplete input. All right, I think it's all right. Good, it's working. Okay, so all right, so good. I think there was. Oh, sorry. I think it's or just ignore that at the bottom. I think it's because of the hash marks, the number signs that I'm putting there. All right, so just ignore that for a second. But what we have here is we have our first 5 rows. And so what you can see here is that these are the first 5 rows. So these are the actual original values. This is not data that has been standardized in any way. Now, if you remember, the input for our linear regression model should be data that has been standardized, okay? And so let me go ahead and get rid of this and just move it along. All right. And so what we want to do is we want to also get the labels from our housing labels. Now remember, housing labels also isn't data that has been standardized. So this is the housing labels. It has not been standardized in any way whatsoever. So it's also data that has not been standardized. But remember, we want our attributes going into the model to be standardized. And so because of that, what we're going to go ahead and do is we're going to pass in those attributes to our pipeline, our full pipeline that we have right over here. So our full pipeline that includes the column transformer, and the column transformer will call the num pipeline, the pipeline that we originally created, and it'll return basically a stratified, not a stratified, but a standardized version of our first 5 rows. So it's going to prepare those first 5 rows, right? And so at this point, what we had now is we have the labels as the original format, which is what the input that we gave right over here. And then it's going to give the data, the first 5 rows, in a standardized format. And so that's what we want there as our input for prediction. Okay. So now that you understand that, let's go ahead and uncomment that. Let's go ahead and comment it here. Okay. So now we're going to get our prediction. So we're going to call the linear regression model, the object that we created right over here. And we're going to call the predict function on that. And we're going to pass in our prepared data. So our data that has been prepared. And you might be wondering, shouldn't the model work without preparing the data? Well, remember, the model has already received data in the input that has been prepared. And so in order for the model to map it to the actual values, it would need data that has been prepared. But thankfully, since we have a pipeline that we can simply call that pipeline every time we receive input data, and we can transform that data into data that has been standardized, that will be standardized, essentially. All right, so we're going to call the predict function, and we're going to pass in our prepared data. Okay, so now that we pass in the prepared data, what should the output be? Well, the output should be the housing labels, again, in a non-standardized format like we have above. Okay, let's go ahead and print out those predictions, get rid of that print statement over there, and print that out. All right, so you see those predictions right over here. These are our predictions. Okay, you can't really say much right now. But what these predictions are, remember, you might be thinking, okay, this is the prediction for first row, second row, so on and so forth. So why don't we just go over here, take a look at the median house value, and compare it? Well, remember, the data that we have right over here is data that has been stratified, because remember, we originally stratified our data. And so because of that, the column values don't necessarily, the row indices are not in the same order. So this value that we might have right over here, I think is a part of row 12,000 or something, right? It could be a part of any row because we stratified the data initially. And so that's why we were able to bring this data. We stratified the data. We went through all the different steps in order to get to this stage. And so now we have to compare that to the labels. What are the actual values? Well, we had to compare it to some labels that we define right over here, some labels from the housing labels there. And we'll go ahead and print out those labels. And so we got the labels here. Now, when we compare these values, you can see here that the house value we projected was going to be 87,000, and it turned out to actually be 72,000. And then we projected it was going to be 31,000, and then it turned out to be 27,000. I mean, 27,000 and 31,000 are pretty close. 14,000 or not, 148,000 or yeah, 148,000. And this one's 82,000. That's pretty far off. So this is not a very good output, right? And so there's different ways. In the next lesson, we'll actually go further into how to calculate the error. And just by looking at this, you can tell that it's not very accurate. But keep in mind, is this necessarily the best way to predict error? Well, obviously not. Why is it not the best way to project error? Well, because my sample size is only about 5 of the 5 rows. You can't project, you can't generalize to an entire population of 30,000 or 40,000 rows just by using 5 rows. And so we took a small sample size and then we were able to project from there. But that's not necessarily representative of the entire population. And so because of that, this is not a very accurate way. In the next lesson, we'll discuss how to find a more accurate way of projecting how inaccurate it is. But just by looking at this data, we can see that it's not very accurate. Now, there is a way to calculate a percentage of inaccuracy. It's called a mean absolute percentage error. And basically what this does is essentially, it basically finds what's the percent difference between our predicted value and our label, right? It finds that difference. And the way you do that actually is, it's a very simple calculation. So for example, for the first column, you would say 87,010 minus 72,100, and then you divide that by 72,100, right? And what that does is basically final minus original over original, essentially, is an equation, right? Basically, in this case, it's going to be prediction minus label over prediction. That's going to give you the percentage error for that particular row, right? Basically, if you substitute it into this, that's going to give you the percentage error. Now, when you find this percentage error, what you can do is you can find the percentage error for every single prediction and label, every single corresponding prediction and label. Sorry about that. All right, yeah, every single prediction and label. So you're going to find it for every single prediction label. So in this case, you're going to say 312,666 minus 279,600, all divided by 279,600, right? And so on and so forth. So let me just put dot, 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 and then we'll go ahead and say 242,269 minus 238,300, all divided by 238,300, right? And so you're going to go through every single row, every single prediction. And then what you're going to go ahead and do is you're going to get a percentage error, right? So you're going to get a percentage error. And then what you're going to do to each of those percentage errors is you're going to average them. So let me call this percentage error 1, percentage error 2, percentage error 3. And then what you're going to go ahead and do is you're going to average these percentage errors. So you're going to say percentage error, well, in this case, it's going to be percentage error 5, right? This is going to be the last one. Percentage error 1 plus percentage error 2 plus dot, 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 plus percentage error 5. And then I'm going to divide that by the number of errors that we have, which is 5, right? And then I'm going to get something called a mean absolute percentage error. What the mean absolute percentage error is it's going to be the average of the error of each of these individual instances. Now, in our case, I already did the calculation, and we got 35.2%. 35.2%. Okay, so 35.2% is the error. But does this mean it's the error for the entire for our entire data frame? No, it's just the error for the first 5 instances of our stratified housing data frame that has been converted into a right? Not converted, but in this case, just the first 5 instances of a stratified version. Okay, so again, that's not very good just by looking at that. But again, in the next lesson, we'll take a look at how to analyze it more thoroughly, just instead of looking at just the first 5 instances. But we covered several things in today's lesson. I feel like we covered how to calculate what the linear regression model first of all is,